Welcome back to our heat transfer class, where we are delving deeper into the fascinating world of thermal energy exchange. This video was made with the support of InnoEnergy. Remember that the introduction to heat transfer is divided into several lessons. For Lesson 9 about the analysis of heat transfer problems, you can find topics 1 to 3 in the video for the part 1 of this lesson. Let's continue lesson number 9 by analyzing, through a calculation exercise, how to use the energy conservation equation in an open system.
In one stage of an annealing process, 304 stainless steel sheet is taken from 300 Kelvin to 1250 Kelvin as it passes through an electrically heated oven. Steel mass flow rate is m and its specific heat is Cp. Height, width, and length of the oven are given in the table. Assume all the walls, the ceiling, and the bottom of the oven at the same temperature Ts. The outer surfaces of the oven have an emissivity of εs, air and surroundings are at the same temperature. The oven is on a concrete bank of thickness Tb and bottom temperature uppercase Tb. Calculate the electrical energy input required for the oven. Make the following simplifying hypothesis. Steady state. One-dimensional flow at the concrete base. Uniform and constant properties. Negligible changes in kinetic and potential energy. Stop the video now and try to solve the exercise on your own. Have you solved this exercise on your own? Despite many simplifications, this is a complex problem. Apply the energy conservation equation in the control volume marked by a dotted line in the figure. The stored energy is 0 because the oven is operating in the steady state. The energy generated per unit of time is the electrical power. For inputs and outputs, start by calculating the input and output enthalpy for the stainless steel sheet, considering that there is no phase change. As output, consider additionally the heat losses by convection, radiation, and conduction. Finally, the energy conservation equation can be written substituting each of the energy terms. The electric power needed is the sum of the energy needed to heat the steel sheet or useful energy plus the heat losses by convection, radiation, and conduction. Start calculating the useful heat. The result is really very high, hundreds of megawatts. For calculating losses by convection and radiation, you need to calculate first the external area. The outer area corresponds to the 4 walls and the ceiling. Now, because the external surface is at constant temperature, you can apply directly the Newton's law of cooling to calculate convection losses. For the losses by radiation to the surroundings, apply the equation for a small surface surrounded by a very big surface at uniform temperature. Remember that temperatures must be in Kelvin. Losses to the ground can be calculated as the conduction through the concrete pad. Assume one-dimensional flux, steady state, without generation and with constant conductivity. Finally, the sum of the useful energy and the thermal losses equals the electrical power of the oven. Now, you can calculate the thermal efficiency of the equipment, which is the useful energy divided by the total energy consumed.
Let us finally move on to the application of the energy conservation equation to a surface.
Calculate the outer surface temperature, T2, and the heat flux through the glass of a window during a winter night, using the data given in the table. To calculate T2, the starting point is to write the energy balance in the outer surface of the window. This is a surface balance. The sign criterion can be to consider all components as inputs. Some will be positive and others negative. Because this is a flat wall with one-dimensional conduction, you can make the balance using heat fluxes. Using the equations already known for conduction, convection and radiation fluxes, the result is a single equation that you can use to calculate T2. Alternatively, you can consider all components in the same direction. In this model, the conduction heat flux equals the sum of the convection heat flux and the radiation heat flux. Take into account that this is only a hypothesis or a way of writing the conservation equation and the difference of temperatures. Therefore, like in the previous case, some components will be positive and others negative. Note you must write temperature differences in the direction of the arrows in the figure, as inputs or as outputs. Note that both sign criteria will lead to the same equation. Solving this equation, with all temperatures in Kelvin, you can find the temperature of the outer surface of the window. After that, you can calculate the heat flux through the window.
Remember that the introduction to heat transfer is divided into 9 lessons. Review some of these lessons if you still have questions about the fundamentals of heat transfer.
Don't miss the videos about more advanced concepts in heat transfer.